So in this video, I'm going to talk about wireless networking and why wireless systems turn out to, in practice, be really different than wired ones. One of the big challenges you see today on the internet is we all want to connect wirelessly, yet there have been a lot of assumptions made historically that networks would behave like wired ones, and actually bridging that to wireless is often difficult, which is why we see poor performance, say, on your laptop using Wi-Fi. So in this video, I'm going to talk really about why is wireless different? What are these properties that make it so challenging and so difficult? And why does it sometimes seem to be flaky? So in the context of this video, I'm going to focus on access point networks. And by that, I mean wireless networks where, say you have your laptop with some Wi-Fi card, and it connects to some access point, which then has a wired connection to the internet. And this access point is serving, often multiple devices, like here's your phone. This is different than, say, a mobile phone network or 3G or 4G, which are managed very differently, much more tightly controlled. All kinds of different issues emerge in those systems. Here I'm just going to focus on open standards, access point networks, things which you just plug in at home, connect to your wired connection to bridge to the broader internet. So one of the first things to realize about wireless is that unlike in a wired network where the medium, the wire, is completely under your control, there's nobody fighting you for the capacity of that wire, it's for you and you alone. In the wireless environment, you're using space, right? Using the electromagnetic spectrum around you, which everyone else might be wanting to use as well. It's not a controlled medium, it's a shared medium. And so in practice, what this means is that it is very tightly regulated. So this is a map of how, just in the United States, radio spectrum is allocated. So radio spectrum, here's kind of the big picture of RF, or not of RF, but of electromagnetic spectrums, down from very low frequency stuff all the way up to cosmic rays. That's this big thing down at the bottom. So this is, you can get this from the US Department of Commerce. This is a free government document. And so generally data communication is occurring in this region down here, different kinds of communication, either data communication, voice communication, etc. Up above, what's in this picture here, this yellow region, is infrared. Then here's visible light here. So here's visible light, here's ultraviolet, X-rays, gamma rays, etc. But RF is down here, so below visible light, lower frequencies. And here's what the spectrum looks like. And so you can see there's a huge chunk of spectrum, right? It's going all the way from 3 kilohertz, so when you have 3,000 waves per second, up to 300 gigahertz, or 300 billion waves per second. So if you recall, if given that RF, or that electromagnetic radiation, moves at 1 foot per nanosecond, at 3 kilohertz, you're looking at waves that are on the order of 300,000 feet long, whereas down to the 300 gigahertz range, you're looking at waves that are 1/300th of a foot long. So a huge range of frequencies for all kinds of things. There's TV, there's radio, there's data communication, there are maritime systems, there are military systems, there are satellites, etc. But when we talk about access point networks and modern data communication systems, we're talking about these 4 narrow chunks. So these green ones are telephony. So this is down the 800, 900 megahertz range, 700. This is the 1.9. Telephony, WiMAX and stuff starting to move up, but basically 3G standards are down here. And these 2 blocks here, these 2 red blocks, this is Wi-Fi. And so when you think about all of the data communication that we use today, phones and laptops, it's all squished in these 4 tiny little slices. Now, the really important thing to realize about wireless is that, as you can imagine, wireless transmission is not a wire. The wireless medium is not a wire. And what this means is that, unlike something propagated on a wire where there's some attenuation or there's some resistance in the copper, a wireless signal is radiating over space. Like in the simplest, if you have a perfect omnidirectional antenna, it's radiating in basically, so if you think of it as in a sphere out. And what this means is that the signal strength degrades with distance at r squared or faster, right? A signal when you are twice as far away from a transmitter, the signal is at least attenuated by 75%. It's at a quarter of the strength, just because think of the surface of a sphere. And so what this means that unlike in a wired system where we can know, oh, well, the cable, as long as it's good and it's not longer than 100 meters, we're going to have a strong signal strength. In wireless systems, you often have very weak signal strengths. In fact, people are going to try and get all the way to the edge because they want to be sitting out, on the lawn using their Wi-Fi access point. Furthermore, unlike a wire where it's tightly controlled, there's nobody doing stuff, wireless is out in the world around you. So it can be that somebody steps between you and your access point. Now suddenly all these wireless signals have to go through that person. They're a big bag of water. The wireless is going to become much, much weaker. And so the signal strength is going to change significantly over time as people open doors, people move around, as you move around, as the humidity changes. Furthermore, everyone else is using the medium as well. There's lots of interference. It's not like you have this wire to yourself. Instead, the person next door might be using their wireless network, which is on the same frequency. So let's look at the first of these, signal strength. So the problem here is that there are obstructions in the real world, and they can move around, and they weaken the signal. If you stand behind a metal plate, your wireless signal will be much weaker than if you stood in front of it. Furthermore, wireless signals reflect, and so it can be that I'm standing, in some hallway here with my laptop, and there's an access point here, and it might be that the signal I get is some weird reflection off of different media, off of different walls. And the trick here is that in practice, this means that, for example, here I'm getting this reflection, but I'm also getting a direct signal, say, through these walls, is that unlike in a wire, in a wireless environment, you can have something called multipath, that you're getting this signal, but you're getting multiple copies of it across different paths with different delays. Think of it like echoes in a canyon, where there's the direct sound you hear, but then all of these echoes taking different paths reflecting off the walls of a canyon. There's no perfectly uniform antenna, so if you move a little to the left, it could be that that antenna is no good and that's actually much weaker where you are, so suddenly the signal goes down and you lose connection. Furthermore, all these things are continuously changing. You can imagine you move a little bit and suddenly the multipath changes, the reflections change. You can imagine I move a little bit, the antenna is a little different, it's oriented differently. And so things are dynamically changing. The environment around you, it's not controlled. It could be somebody closes their office door and suddenly your wireless signal goes out. Just to give you a sense as to what this looks like. So this is some data collected by a student of mine who's now faculty at Ohio State, Kanan. And what it's showing you is signal strength over time down here on the bottom, what's called the received signal strength indicator, signal strength. And then the top, the observed packet reception ratio. So this is for an 802.15.4 link that he measured. And so the transmitter is stationary, the receiver is stationary, and for every packet he received, he logged what was the received signal strength, and then he was observing what percentage of packets were received over time. This red line shows the long-term average of this communication. So it's actually pretty good, around 93%. But what we can see is that over the space of just a couple of seconds, the signal strength is pretty solid up at 84 dBm, that's the units. It drops down a little bit, things get a little worse, drops down, and then suddenly it drops, and it just drops by around 6 or around 8 dBm, or around 8 dB. So around a factor of 10 or so, or 5 to 10. And then what happens is that is below the signal strength at which this device can receive packets, so the packet reception ratio drops to 0% for a short period. Then it comes up and starts receiving packets again. And so just over the space of 10 seconds or so, we see that a link is going from 99% down to 80%, down to 85%, back up to 90%, down to 0%, to 70%. You see these significant changes over time. And so somehow your network, think about TCP, think about all these retransmission schemes, has to deal with this kind of behavior. So here I'm going to show you, in fact, a real-time video of a network we had deployed here at Stanford called SWAN, the Stanford Wireless Access Network. It's an 802.11bg testbed, so Wi-Fi. And it's around 25 nodes or so. And essentially, what I'm going to show you is what this network looked like over 2.5 seconds. So this is in a time steps of 25 milliseconds. So there's 100 time steps. And each of these is a node. Gates is the computer science department. Packard is the EE department. There's this street in between, Sarah Mall. And I'm going to show you what this network looked like over time. So for each node, there are lines between nodes which show you the packet reception ratio here of those links. A dark line means that all the packets are received, and a very light line or no line means that no packets or very few packets are received. So watch what's happening with these links, how quickly they're changing. Remember, this is 2.5 seconds. And so we can see links are coming and going. They're changing, in the space of 25 milliseconds or less. Like look at this link here and how it's oscillating between 80% and 10% back and forth. And look at the links between the two. So the point here is that in wireless networks like Wi-Fi networks, they're highly, highly dynamic. So in addition to this issue of just signal strength changing over time, there's also the issue of interference. So a lot of wireless communication today is occurring in unlicensed, like Wi-Fi, its access point networks occur in unlicensed bands that don't require a license from the government. Anyone can use this band, and that's why they're so popular, because they're free. But then lots and lots of different technologies share the band. So here's a map, for example, of just what's going on in the 2.4, basically the 2.5 gigahertz range. This is Wi-Fi's lower frequencies. You can see here's Wi-Fi 802.11b, and these different ranges here. You can see its bandwidth of 22 megahertz. Here's channels 1, 6, and 11. But at the same frequency ranges, there's 802.15.4 Zigbee, a low-power wireless system, which is using the same range of frequencies. Bluetooth uses the same range of frequencies. So this means that something in 802.11 can receive interference from something in 802.15.4 and vice versa. These are challenges that all these systems have to deal with, that they might have good signal, they might have low noise, but then someone's interfering with them. And so, for example, if you just look at what wireless activity is like over time, this is this nice graph which Om Prakash Kanawali, who's now a professor at University of Houston, generated. This is taken at this data from USC, which is where he used to be a student, PhD student. And you can see, look at all this Wi-Fi activity. So here's time in seconds from 0 to 2 minutes in different Wi-Fi channels, 1 to 11. You can see that these channels 1 and 11 are really, really busy, or orange is showing lots and lots of Wi-Fi activity. And so the lesson to take away here is that wireless networks are becoming increasingly important. We'd much rather just connect to the internet wirelessly rather than plug a wire into our laptop. But generally they don't work as well. They're less reliable, they're more flaky, and this is because of the fact that they're in this shared medium that's uncontrolled. Lots of different devices are using it, the environment's changing around them, and there's lots of interference. And so in practice, what this means is that to try to get wireless to be good enough as if to be usable, do these different properties and different behaviors, wireless actually ends up using very different algorithms and protocols. So wireless link layers look different than wired link layers. Wireless media access control systems look different than wired ones. And so this next series of videos, I'm going to go into some of those differences and explain how wireless today works.